The second video is all about the different transformations that you can make. So we've got 3 that we're going to learn about: translations, dilations, and reflections. So translations are also known as shifts. So really you've got 2 categories. You can either go left and right, or you can shift up and down. So if you picture like the way that an original function is drawn, you can move the graph up, down, left, or right. And doing something like that, it doesn't change the shape or the orientation of the graph, it just repositions it somewhere on the axis. All right, so we've got 2 things that can happen. You can take the original function, so like f of x, and then you can tack on a plus or minus k like that. All right, so if you add k, you're going up. If you subtract k, you're going down. All right, so that would be this many units up or down. You could also do this where there's a value added inside the function. Now let me show you the difference. This parent function has something on the inside. That falls into this category. This parent function has a number subtracted on the outside. That falls into this category. So that's what I mean, like f of x compares to the parent function. Okay, so this is a left or right shift. This is very, very important with the left or right shift. It does the opposite of what you think it's going to do. This one is very counterintuitive. Okay, so example 2, describe the translation in each function. So when you guys are doing these in your homework, on the mastery check, on the tests, you need to write down 2 things. Okay, so you need to write down what parent function it is. So this is an absolute value function. The absolute value bars give it away. If you see those, you automatically know it's absolute value. And then the plus 3 is on the inside of the absolute value function, so that puts it in this category. And the plus 3, remember this is the opposite. Positive makes you think it would go to the right, but it actually goes to the left. So it goes 3 units to the left. Okay, and then when we say graph the function, I mean do a quick little sketch. So you want to compare it to the parent function. Instead of going through the origin, it'll move 3 units over to the left. Okay, so we'll go 1, 2, 3. Once you plot that, you can just do a very generic sketch like that. Okay, let me explain why it goes to the left and not to the right. If you plug in this point right here, let's actually go to this one. If you plug in x equals 0, the absolute value of 0 is 0, which is why it gets plotted right here. If I plug in -3, -3 plus 3 is 0, which is why this gives me a y value of 0. It doesn't shift to the right. If you plugged in +3, 3 plus 3 is 6. So at +3, we should be all the way up here at 6. So that's why it does kind of the opposite of what you think it's going to do. Okay, this one. Start with the parent graph. The x squared means it's a quadratic function. So we start with our original parent graph of a quadratic function. And then this -4 is on the outside of the parent graph, not on the inside of the parent graph. If it was on the inside, it'd be in like parentheses or something. So we're going 4 units. And this one actually does what it seems like it's going to do. So -4 actually does mean it's going to go down. Okay, and then just a quick sketch. So our original parent graph starts at the origin, so we're going to shift it 4 units down. So its vertex is going to be right there, and then just sketch a parabola. Okay, so you can see if you plugged in x equals 0, 0 squared minus 4 means I would have a y value of -4 down there. Okay, so those are translations. The next topic is reflections. Okay, so reflections is like, it's like a mirror image. You can reflect over 2 different axes. Okay, so a reflection is also known as a flip. You can think of it that way. So it can get flipped over the x-axis or flipped over the y-axis. Okay, so when the parent function itself is multiplied by a negative, so if you have like a negative on the outside like that, what that does is it flips over the x-axis. Okay, that's one option. So the x-axis is the one that goes this way, so it's like a horizontal flip. like upside down. If the negative is on the inside of the function, inside absolute values or inside parentheses or something like that, what that does is it flips over the y-axis. So the y-axis goes this way, so our graph would flip over the y-axis. That would be a vertical flip. Okay, so we'll write that down. This one would be a vertical flip. This one would be a horizontal flip up and down. Okay, so let's look at a couple of these. This, we have the negative absolute value of x. It is not inside the grouping symbols, it's outside the grouping symbols. So that falls into this first category right here, so it flips over the x-axis. All right, so we start by writing what type of function it is, because this is to describe the reflection. So we start by writing what the parent graph is, and then what's happening. So we have a reflection over the x-axis. Okay, so go ahead and set that up. So normally my absolute value goes like this, but I'm taking it and I'm flipping it upside down. So this piece that was right here gets flipped upside down like that. Ignore that, that was an accidental pen mark. And this piece right here gets flipped over the x-axis, so it looks like that. So it literally just looks like it got flipped upside down. That is my new graph with the reflection in place. This right here, you can either think of the negative being on the inside or the outside. Either way, this is a linear function, and it's a reflection. Let's just call it over the x-axis, since there really aren't any parentheses or anything like that. If the negative was inside a set of parentheses, or if it was inside the absolute value, that would be a reflection over the y-axis. All right, so normally my linear function looks like this. If it gets flipped over the y-axis, it looks like that. However, the reason that I wasn't too picky about whether we said x or y is because if it looks like this and it gets flipped over the y-axis, it looks like that, which is the exact same graph either way. So our new graph is going to look like this. It got flipped. So you can either consider this piece to be flipped over the x-axis, become this, and then this piece would get flipped over the x-axis to become this, or you could have pictured it this way. So here's the original. You could picture this flipping over to the y-axis to here, and picture this flipping over the y-axis to here. Either way, you're going to get the same answer. So that particular one could have been an x or y-axis flip. Okay, dilations. Dilations are stretches or compressions. They shrink or they enlarge a figure. All right, so make it, double its size or half its size or something like that. All right, so this either shrinks or enlarges the graph, depending on what you're given. Okay, so depending on what you multiply in, we've got a couple things that could happen. So you could multiply like a times f of x, something like that. So I'm going to write a times f of x that you're actually multiplying something in. What that does is it stretches a value vertically. Okay, so two different things. So it stretches vertically if a is greater than 1. And then we call it a compression if it's a value between 0 and 1. Okay, so if it's like a fraction, it compresses it. So picture it this way. A vertical stretch means you're stretching this way or compressing this way. If you multiply by 2, picture something stretching to twice its original height. Whereas if you multiply by a half, something would be shrinking or compressing to half its original height. So that's what those numbers will do. Let's practice some of these. 2x squared, that is a quadratic function. The x squared gives it away. And then it is stretched vertically, we say by a factor of 2. All right, so think of your original quadratic. You've got a parabola right in here. If you were to stretch it, think if you stayed all your same dimensions, weight and everything like that, if we stretched you out to twice your original height, you would get very, very skinny, probably uncomfortably so. So when you stretch it by a factor of 2, it's going to get narrower and taller, kind of like that. So it's like stretching the parabola up. So it's going to look skinnier when you see it. This next one right here is absolute value. Again, the absolute value bars themselves give it away. This is 1/3. So 1/3 means it's compressed vertically by a factor of 1/3. Okay, so picture if we made you 1/3 your original height, it would squash all your mass out. You'd be a little bit plump. Okay, so picture where the normal absolute value graph is. If we compress it vertically, it's going to look a lot wider, like that. Okay, so that's what a dilation looks like. In the next example, we're going to combine a whole bunch of them and see what the original would look, or what the new one would look like. Okay, so starts as a quadratic function, and then we're going to describe all the transformations. Okay, so this negative, we'll start with that, kind of move left to right. This negative is on the outside, so what it's going to do is it's going to get flipped over the x-axis. The 1/2 is a dilation. Since it's a fraction, it's going to compress by a factor of 1/2. I mean, that is times, not as x. Compress the graph times 1/2. This -5 on the inside means it's either a left or right move, but if it's on the inside, remember it does the opposite of what you think it's going to do. So it's going to move 5 units to the right, which is counterintuitive. That minus seems like it should be left, but you do the opposite when you see something inside. And the plus 12.5 on the outside means you are moving 12.5 units up. Plus actually is up. That one does exactly what you think it's going to do. All right, so we wrote everything down. Now we're going to graph it. So your normal quadratic function will start right at the origin. This one is going to move 5 units to the right and then 12 units up. So let's go 2, 4, 6, 8, 10, 12. So we're going to go 12.5. So it's going to start right here. Sorry. And then it's going to flip over the x-axis. So that flips it upside down. And it's going to be compressed by 1/2. So it's going to be nice and wide, and it's going to be flipped upside down. So it's going to look something like that. Which, if you read the description, that should make sense. A parabolic archway. You can't go under an archway if it's flipped right side up like an original parabola would be. Okay, we're going to do these really, really quickly. Translations, if it's on the inside and you actually have plus h, you're going h units to the left. Remember, the inside is counterintuitive. And if it's minus h, you're going h units to the right. Those left-right units are the opposite of what you think they're going to do. If you have plus k on the outside, you're going k units up. And if it's minus, you're going k units down. Okay, we've got 2 different flips here. If the negative is on the outside of your parent function, that's a flip over the x-axis, meaning it's a flip up and down, like that. If the x is on the the negative is on the inside, you flip over the y-axis. So it's like a left and right flip. This is like flipping it up and down. This is like flipping it left and right. Okay, so over the x-axis versus, over the x-axis like this versus over the y-axis like this. Okay, and we've got 2 different types of dilations. If the number is on the outside and it's bigger than 1, this is a stretch vertically by a factor of a. And then if a is somewhere in between 0 and 1, this is a vertical compression Okay, and then this one, even if it's on the inside, this is a stretch by a factor of B. Oops, it's by a factor of A. And this is a compression by a factor of B. All right, so 3 different categories that you can fall in. So make sure you practice these because the little tricks like this and when to go up and down versus left and right can be a little bit complicated.